Mr. Heffernan, here's a short video on centripetal motion, loop-de-loop problems. So loop-de-loop is a vertical circular path, and which of course we call loop-de-loop. And you can see a plane may travel around like this, okay? Or you may have a roller coaster situation like this. And in combat, fighter pilots will feel up to 7 Gs in combat. Some dangerous roller coasters will have 6 Gs for 1 second. Anything more is considered illegal, and even that is pretty extreme and pretty dangerous for some people. At 10 Gs, everybody passes out. So let's take a look at those G-forces in a loop-de-loop. So when you take the loop-de-loop, you're going to feel different amounts of apparent weight at the bottom, going up at the top, and coming back down. So for example, let's say we have a fighter pilot doing a turn at 50 meters per second, which is Mach 0.147 approximately. And let's make it a 500 meter turn, half a kilometer. What are the G-forces at the bottom, side, top, and side? Okay, so at the bottom, you have the force of gravity pulling you down, and then the seat bottom pushing you back up towards the center of the circle. So the centripetal normal force is what you're going to feel. This is the seat pushing on you, fighting your inertia. So if you take the normal force, which is the blue arrow, and subtract the red arrow for gravity, you're going to get the green arrow. This is your unbalanced amount of force providing centripetal motion. So we're going to have the normal force towards the center, gravity trying to pull you out, which is positive. And then we have mass times centripetal acceleration, which is negative v squared over r. And so we're going to replace the force of gravity with mg. And then we want to get an mg on the other side as well. So what we're going to do is multiply by g over g, which is just a 1. So now we can get an mg, bring the other mg over, and now we have an mg and another mg right here. So we can factor the mg, and we're going to be left with 1 plus v squared over r, or better if you write v squared over r plus 1. When we sub in our numbers, 50 meters per second squared, which is 2,500, divided by 500, we get a 5, and then we're going to add the 1. So if you're at the bottom of this loop-de-loop here, you are going to feel 6 mg, or 6 times more than your normal weight. So if you are a 200-pound pilot, you'll feel like you weigh 1,200 pounds. If you're a 100-pound pilot, you'll feel like you weigh 600 pounds. So you're gonna feel quite the G-forces. It'll be pretty hard on you. Now, what if you get to the top of the loop? Now, the normal force and gravity are both pulling you towards the center, and so they're going to combine to have a net unbalanced centripetal force towards the center. So the only difference, if you work through the math, is instead of having a positive 1, you will get a negative 1. And when we sub that in over here, we'll get 5 subtract 1, which is 4 Gs. So a fighter pilot will feel 4 Gs at the bottom of this loop, which is exactly 2 Gs less than the bottom. So in a loop-to-loop, you will get your maximum Gs at the bottom and your minimum at the top. And if you do maintain a constant speed, there'll be a difference of exactly 2 Gs. But in real life, like a roller coaster, you actually have less speed as you go up, so there's even more of a difference. So how about the side going down? So in this case here, only the seat is pushing you towards the center, and gravity is no longer involved in the centripetal direction. It's straight down or tangential to the circle. So now your unbalanced force is completely 100% the normal force. So now there is no plus 1, there is no minus 1. It's just the normal force, and we get 5 mg altogether. So if you're a pilot and you're coming down in this situation, you'll feel 5 Gs on the side coming down, 4 Gs at the top, and 6 Gs at the bottom. Now how about going up? Going up is actually a little more complicated. Your centripetal force from the normal is the same. It's not going to change. It's still going to be the 5 mg. But now, gravity's pulling you towards the back of the seat, So now you have another normal component pushing you upwards. So now you're going to have the back of the seat providing 1 g of force, the seat of the seat providing 5 g's, and you notice they make a right angle triangle, so we have to use Pythagorean theorem. So we get 1g squared plus 5g squared square rooted 5.099 mg. So the pilot's actually going to feel 5.099 g's on the way up, slightly more than coming down. Now, when it comes to roller coasters, there is another option besides the circle. You can use something called a clothoid. How are they beneficial to amusement parks? Well, clothoid loops function at a slower speed. So they can be the same height as a circular loop, but still manage to work at a slower speed. They're a little less wide, same height, and slower. So for example, if you had a circle which needed a speed of 150 kilometers per hour, you divide by 1.4, a clothoid would get away with only 107 kilometers per hour. So if you, when you build it, you can, instead of having a larger hill, you can have a shorter hill to achieve the same thing, and you can save park space at the same time. Okay, so loop-to-loop is a vertical circular loop, or occasionally a clothoid. The maximum g's occur at the bottom of the loop, and there's approximately a 2g difference between the top and the bottom. It's exactly 2 g's if you have constant speed. And a clothoid loop is an alternative to the circular loop, and it is more cost effective for amusement parks. So I hope this helps. Thank you.